Today we're taking a look at section 12.5 on the normal distribution. And first of all, we take a look at two different kinds of random variables. We begin with the discrete random variable, which is a variable that may take on only a finite number of values. And so what we'll do is we'll begin with an example that we've looked at before. We have a family with 3 children, and what we want to know is the number of girls in the family and what probability will be for each of those numbers. So as we look at the girls, we can see we go from 0 girls, where we have boy, 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 1 girl, 2 girls, and 3 girls. So 0, 1, 2, and 3 are the possible values for our x, and x is representing the number of girls in the family that has 3 children. Okay, so let me see if I can get my pen to come back here. Okay. Alright, so as we look, I got these from a tree diagram. I did the first child, the second child, and the third child, and then I followed the branches to get girl, 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 boy, girl, boy, girl, girl, boy, 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 girl, girl, and so forth. So, how many of those, what's the probability that a family of 3 children will have no girls? Well, we only have one case of no girls. So that means 1 out of, and it's a total of 8. For 1 girl, we have 1, 2, 3 possibilities out of the 8. For 2 girls, 1, 2, again, 3 possibilities out of the 8. And for 3 girls, we only have this one case. So again, it's 1 out of 8. Now what you'll notice is the sum of these probabilities is equal to 8 eighths, or 1. This is what we call a probability distribution. Probability distribution can be a graph or a table or some equation that describes the probability and how it's calculated. So this is an example of a discrete probability distribution. It's not possible to have the fractions because we're talking about the number of girls. It would have to be 0, 1, 2, or 3. It couldn't be 2.5 or 1/3. So 0, 1, 2, and 3. Now when we graph this, and we do want to take a look at graphing. Let's see, I think I'll just put the fractions on here. 1/8. Of course, 2/8 would be 1/4. 3/8. And then 4/8 would be 1/2. So here's our probability on the vertical axis. On our horizontal axis, what we're going to have is the number of girls. Okay, so families with 3 children, we want to give that a name. Okay, so we're going to start with a bar for 0, a bar for 1, bar for 2, and a bar for 3. Okay, so what we have is 1/8 for 0. That's our first bar. 3/8 for 1. For 2. Ooh, and these are very crooked. Okay, hopefully you can use graph paper and a ruler. 3/8 also for 2, and then back to 1/8 for 3. So this is what our distribution would look like. Let me erase this so it looks a little bit better. Right in here. Alright. So that's what we would do with a discrete random variable. Okay, so it's a finite number of values. In this case, we had 4 different values. All right. We also look at cases that involve the second type of random variable, which is a continuous random variable. These random variables can take on values along it's an infinite number of values along a continuous scale or range. And these are ones that we concentrate on in section 12.5. They do introduce us to this discrete probability distribution, but most of the time in this section, as you can see by the name, the normal distribution is spent on the continuous random variables. The normal distribution is an example that encompasses is a part of continuous random variables. And what we find is in the normal distribution we have a bell-shaped distribution. If you remember, we talked about the empirical rule back some sections ago, and many things that we look at in nature have normal distribution. So if we're looking at the heights of trees, the weights of different animals or adults, if we're looking at anything that's occurring in nature, perhaps blood pressures, heart rates, a lot of these will fall into a normal distribution. So they will be a bell-shaped distribution. IQ scores is one of the cases that's probably most commonly known. So what are some properties of the normal curve? We know about the 34% and the 95%, 99.7%, and and so forth in terms of within one standard deviation we have the 34%, within 2 we have 95%, and so forth. So we know that already. Well, we have some other properties that we should mention. The graph of a normal curve is bell-shaped and symmetric about a vertical line through the center. So symmetric means it's the same on both sides. So if we were to fold our graph along the line in the middle, we would find that the graph would meet on our paper. The mean, the median, and mode of a normal distribution are all equal, and they occur at the center on that line where I was talking about folding. The empirical rule applies. About 68% of all data fall within one standard deviation of the mean, 95% within 2 standard deviations of the mean, and 99.7% within 3 standard deviations of the mean. So let me add our curve, and you'll need to add it on your notes as well. And what we find is that the graph out here at the ends is going to get closer and closer to this x-axis, if you please, but it will never touch it or cross it. So it's going to get closer and closer, but it keeps going on and on. So what we're looking at within one standard deviation, as mentioned, 68%. All right, that's our 1. For 2, we have 95%, goes out to there. And then for within 3 standard deviations, we have 99.7%. Okay, so that's what we're talking about. Now, as we move into this chapter talking about the normal distribution, what we will be looking at is actually the z-score, as opposed to, and these should be means here. So you may want to add your x-bar so you don't get confused on that. We'll actually be looking at the z-score. So when we say a z-score of 1, we're saying we're 1 standard deviation above the mean. 2 means we're 2 above, 3 means we're 3 above, -3 means we're 3 below, and so forth. Okay, so, all right, meaning of the normal curve areas. In a standard normal curve, the following three quantities are equivalent, and they're used interchangeably. The percentage of total items that lie in an interval is the same as the probability of randomly choosing an item lying in an interval, and that is equivalent to the area under the normal curve along an interval. In calculus, you can actually compute these areas using the formula for the graph of the bell curve. For us, we'll be using a table. Okay, so the area is equivalent to the percentage, which is equivalent to the probability, and we simply write the probability as a decimal. So area and probability are expressed as a decimal, and the percentage of items is the other way to represent it. So what we need to remember is our z-score formula. Our z-score formula says that x minus x bar divided by s will give us our z-score. And it'll give us the number of standard deviations. Our value x lies above or below the mean. And on page 671 there is a table that table 17 that represents the areas under the standard normal curve, and we'll be using that table to help us solve problems. So I would highly recommend that you watch the sample problems, because this is probably a new subject for you, and I'll show you how to use the table to find answers to a lot of different types of questions in the sample problem section.